Over the past few decades, it has become quite obvious that humans are not the only living organisms with intelligence. However, the story of intelligence I am about to tell does not start with them. It goes back 13.8 billion years, back to the moment the universe was born, the Big Bang. It's a story of time and space, matter and energy. It's a story of unfolding. It's the story of how the very nature of the physical universe, from its very inception, led the universe to get to know itself and eventually to reflect. Here's how that story goes. There was a time when there was no time. There was no space. There was nothing. Then there was a bang, a big bang. It exploded from the teeny tiniest point of nothing into everything. All matter, all time, all space emerged from this point. All the galaxies, all the planets, all life, and intelligence had their genesis at a single point in time. In the first fraction of a second following the Big Bang, the cosmos was 1 trillion times 1 trillion times 1 trillion more dense than water. Its temperature is estimated to have been 10 to the power of 21 Kelvin. As reported by Dr. David Baker at Macquarie University in Australia, within that ultra-dense, ultra-hot soup, there was almost no complexity during these first few seconds. The material that comprised the universe was uniform. Without the ability of this matter to clump together, there could be no physical structures through which energy could flow. And without a flow of energy, there could be no complexity. But a fraction of a second later, 10 to the power of minus 35 seconds following the Big Bang, we find that things had changed. Things were beginning to get interesting. We know this as a result of 3 NASA space missions, which were designed to measure the diffuse, infrared, and microwave radiation that were present in the early universe. The cosmic microwave background spectrum was measured with a precision of 5,000ths of 1%. Based on the data from these missions, Dr. Baker says that when the universe had expanded to the size of a grapefruit, at the level of subatomic, ultra-small matter, there were tiny particles such as photons and electrons popping in and out of existence. This is the area of physics known as quantum mechanics. Usually, these virtual particles are too small to have any impact on the universe at larger scales. But during the earliest phase of cosmic inflation, this activity set the stage for everything that followed. This infancy had the potential for 2 very different types of outcomes. If, during the first fractions of a second following the Big Bang, quantum fluctuations had been evenly distributed, the adult universe which followed would have been smooth. Matter would have been evenly distributed as the universe expanded. The universe would have been exactly the same everywhere at all times. But this isn't what happened, as we can see here from this microwave photograph taken by NASA. Instead, the quantum fluctuations were not evenly distributed. They were not smooth. In simple terms, there was a tendency for particles to clump together unevenly. The unevenness of the distribution of matter at the quantum scale is responsible for all the increasing complexity that followed in the next 13.8 billion years, because in time, those tiny variations would lead to much, much larger aggregations of matter. Hydrogen and helium in stars, which in turn would produce chemical elements, planets, and life on Earth, including us. All that came from a tiny blip, a quantum fluctuation in the relative density of matter that happened in a sliver of a second, right at the beginning of space and time. In other words, the potential for life was present from the very beginning of the universe. It was woven into the very fabric of the matter that comprised the universe, making it likely that more and more complex forms of matter would evolve over the billions of years that followed. During those billions of years, galaxies formed, including our own, the Milky Way. Our sun is located near its edge. In the process of the sun forming, gravity attracted nearby matter, forming the planets that now circle our sun. One of them was the Earth, the planet we live on. Well, let's not get ahead of ourselves. It didn't look like this at all. Our moon was produced by a forming planet crashing into Earth. The crash resulted in a part of what was to become the Earth ejecting a big piece of itself. Gradually, the Earth began to cool off. It formed a crust which floated on its surface. As it cooled, its chemistry changed. With the help of ancient volcanoes spewing ash, it rained and it rained, producing our oceans. And in those oceans, an amazing thing happened. It wasn't on the surface. You had to look below, deeper still, to where the heat from the Earth's molten core pushed its way to the surface of the ocean's floor. There, a cauldron of ever more complex proteins was brewing, the building blocks of life. It should be noted that there are scientists who see evidence that this process happened not at the bottom of our ancient seas, but rather near the cones of ancient volcanoes, or in the disk of dust grains surrounding the sun before the formation of the Earth. There are also scientists who think there is a possibility that extensive meteor bombardment of the Earth brought water to Earth from the far reaches of the galaxy, and this is how our oceans were formed. It is possible that meteors also brought the complex molecules that were the precursors to the formation of single-celled organisms, or perhaps the earliest single-celled organisms themselves. It likely will be many, many years, perhaps centuries, until these questions are fully answered. What we do know is that the earliest evidence for life on Earth comes from fossilized mats of cyanobacteria called stromatolites. They were found in Greenland and are 3.7 billion years old, though scientists think life probably began even earlier. Other types of bacteria evolved as well. By the time they had evolved to become what most people think of as simple single-celled organisms with DNA, the table of life was fully set with living organisms having the ability to smell, hear, see, feel, move, communicate, and behave. They were intelligent. How that happened will be our starting point for Part 2. In Part 3, we will explore how the sense of smell evolved, starting with single-celled organisms. We will see how increasingly complex forms of life use this ability intelligently to adapt to a wide range of environments. In Part 4, we'll observe the evolution of life's ability to detect, process, and make use of light to solve ever more complex problems. In Part 5, intelligence will be explored in the context of an organism's ability to detect and intelligently make use of vibrations, such as sound, to survive. It will be an exciting journey.
Check Mercury umbilical. Oil evacuate. Mercury umbilical clear. Mercury evacuate. Lights on. All recorders to fast. T-minus 18 seconds and counting engine start. May the wheels be with you, Thomas. Good Lord, ride all the way. Godspeed, John Glenn.
Friendship 7, America's first launch of an astronaut to orbit the Earth, was an amazing achievement, one that has many similarities to the start of life. There were so many moving parts. On launch day, tens of thousands of people worked together in seamless precision, supported by an estimated 2 million people who work for the contractors and subcontractors who developed the thousands of innovations that were required to launch a man into orbit and safely bring him home. And it isn't a stretch to say that none of these inventions could have occurred without there having been thousands of discoveries made during the preceding centuries. Certainly, if NASA scientists thought that the sun and the stars orbited the Earth, this launch couldn't have occurred. Or if Galileo and Kepler hadn't discovered the basic laws of motion, or iron tools hadn't been invented, or agriculture, or cooking, or clothing, or writing, or the taming of fire, or the invention of the wheel. In many ways, that's the story of how cellular life began. There were so many dependencies, only the process didn't occur over a period of the measly 2.5 million years it took Homo sapien to go from inventing fire to the launching of John Glenn into orbit. No, to create a living cell, there were so many steps and so many inventions required that it took 750 million years, give or take a million or two. Beagles are better at using their sense of smell than we are. They have 250 million scent receptors, and humans have a measly 5 million. However, what we have is great transportation. We can hitch our noses to this Atlas rocket and take our comparatively second-rate noses to another planet, to Mars. And when we get there, the extensions of our noses, the Mars rover, will use the tools we installed on it to sniff the ground and even to dig beneath it. We aren't hunting rabbits. Humans are hunting for the scent, the molecular signatures of water and various organic compounds that might indicate that in an earlier time there was life on Mars. But let's now return to Earth and look at two of its earliest life forms, Salmonella and E. coli bacteria. They are more than simply sources of food contamination that can get us sick. They are intelligent life forms that use their sense of smell to survive. What does it mean to be intelligent? Intelligence has three components: information acquisition, information processing, and behavior. Having these abilities greatly increases the odds that an organism will survive and live long enough to reproduce. 2.5 million years ago, the ancient ancestors of E. coli and Salmonella evolved the ability to sense chemicals in their environment, which could help them find food, avoid danger, and reproduce. They evolved receptors which acted like radio antennas that can pick up specific radio waves. The receptors of these bacteria only become activated when a particular molecule, such as an amino acid or a toxin, binds to them. Once a molecular signature is detected by the receptor, this information is converted into electric signals that are sent to its flagella, which are the bacteria's whip-like tails. Signal strength is determined by the quantity of molecules the cell has detected. In other words, how many receptors are bound by a specific molecule. If a toxin is detected, the flagella will move the bacteria away from it. Or, if the bacteria has detected a nutrient, the flagella will propel the bacteria towards it. Our pet dogs do this too, but not with flagella. They have legs. They also have specialized olfactory receptors that are sensitive to the odor of ethylene glycol, a toxic chemical which even in small amounts can cause serious illness or even death in dogs if ingested. Plants have developed their own distinct forms of intelligence through millions of years of evolution. While plants lack brains and nervous systems, they have evolved a range of sophisticated mechanisms to detect molecular clues that allow them to perceive and respond to their environments. One of the key ways that plants display intelligence is through their ability to make decisions using their molecular detecting sensors. Acting like radio antennae, a plant's receptors sense favorable or unfavorable weather conditions, pest attacks, and the availability of water and nutrients. Then, with this acquired information, they produce a wide array of chemicals to respond to these conditions. Some responses are defensive. Some plants go on offense. The Cascuda plant, for example. When it senses the presence of volatile organic compounds, which have been secreted by a nearby plant, such as a tomato plant, it moves in the direction of those scents, like a heat-seeking missile guided to its target. It then wraps itself around the stem and starts to penetrate into its tissue using a specialized probe called an astoria. Quite a tool, like the probe attached to the Mars rover. Virtually all life forms have discovered molecular signatures and evolved sophisticated methods to intelligently use this information to survive and to reproduce. What other properties of the universe has life discovered? What about light? All creatures, great and small, have the energy they need to stay alive, because in the process of life evolving on Earth, one branch of life discovered how to use sunlight to synthesize foods from carbon dioxide and water. Plants. How do they do this? To answer this question, we need to understand what light is. First and foremost, light is energy. Energy that derives, like everything else in the universe, from the Big Bang. Every second, a star like our Sun converts 4 million tons of its material into heat and light through nuclear fusion, a process by which mass is converted into energy. Plants reverse this process, converting the energy of light back into mass in the form of chemical energy. This is the process of photosynthesis. The first photosynthetic organisms were likely cyanobacteria, which evolved around 2.7 billion years ago. Cyanobacteria contain pigments called chlorophylls, which absorb light energy and convert it into chemical energy in the form of glucose starch or carbohydrates. A byproduct of this process is the production of oxygen. Over a span of 200 to 300 million years, the oxygen released by cyanobacteria steadily accumulated over vast swaths of the ocean and oxygenated the water. Eventually, oxygen replaced the Earth's methane atmosphere, leading to the extinction of virtually all life forms on Earth, because they had evolved in a methane-based atmosphere. Through the process of natural selection, they were replaced by oxygen-based life, cyanobacteria. They set the stage for all the life we see on Earth today. The ability of animals to detect light and process this information to guide their behavior evolved 600 million years ago. First, light passes through the cornea, which bends the light to help the eye focus. The iris controls how much light enters the eye through the pupil. The eye's lens works together with the cornea to focus light on the retina, which is made up of specialized cells called photoreceptors. They turn the light into electric signals which travel through the optic nerve to the brain, which turns these signals into images. Let's see how this works for mantis shrimp, which became a distinct species about 190 million years ago. They possess one of the most complex set of eyes in the animal kingdom. Their eyes are mounted on mobile stalks, allowing them to move independently and rotate in all 3 dimensions. As a result, they have a 360-degree view of their surroundings. Their compound eyes functions as separate visual units, each with its own set of photoreceptor cells called ommatidia, which are arranged in a mosaic pattern, providing the mantis shrimp with an ultra-wide field of view and exceptional spatial resolution, perfect for hunting prey in a coral reef and avoiding detection from those organisms that would prey on them. The mantis shrimp has 10,000 ommatidia per compound eye. The dragonfly has up to 30,000. It is a master of motion detection. Owls are masters of motion detection as well, particularly at night. They evolved extra-large eyes so that they can capture more light. Their pupils can reach 2 centimeters in diameter and are packed with low-light photoreceptors. Owls also have a specialized mirror at the back of each eye called the tapetum lucidum. When light goes through the eye's light-sensitive retinal cells and hits the mirror, it is reflected back, giving the owl's photoreceptors 2 chances at catching each bit of light. Their hunting behavior relies significantly on this visual information, which is processed by the visual cortex in their brains. This information is used to track the exact movement of their prey and then to execute a precisely timed and targeted attack. Human beings use their eyes to hunt as well, but they are not as highly refined for this task as an owl's for night vision. We hunt primarily during the day, but now have tools that enhance our natural abilities, making our vision second to none. Our eyes lack the precision of an eagle's, but we can send extensions of our eyes up out of the Earth's atmosphere to explore the cosmos and down into the world of micros and atoms. Our vision extends inwards too, into the realm of the imagination. Yes, other organisms can create internal representations of their environments and then use them to develop solutions to problems, as we see here. But only humans can use internalized images to make art. Our creations can be literal. Or, as is the case of this Oscar Howe painting, the Sacra Y dance, a work of art can be abstract. The viewer's perspective of the ceremonial hunt is from below. Looking up, the hunters appear to swirl and tumble as an abstract rendering of a ritual, which itself is an abstraction. The painting is an abstraction of an abstraction. This evolution of art technique from the time of the first figurative cave painting took 45,000 years and parallels comparable technical advances in other fields of human endeavor that occurred during this period of time, all based on our ability to use light intelligently. We see an arch. We learn how it works. We build an aqueduct. We observe fire. We observe rocks. We mix them together precisely and make steel. We observe plants and see how they grow, which leads to the invention of agriculture and an understanding of heredity, and eventually to the discovery of the genetic code that guides the development and functioning of all life on Earth. whether it is sound conducted through the medium of water or sound conducted through the medium of air. The perception of sound is the perception of vibration. Life forms having discovered vibration are able to answer questions of who, what, when, and where. Being able to answer those questions is crucial to survival and to reproduction. The red-eyed tree frog is able to answer most of these questions through its ability to detect vibrations and use this information to establish and defend its territory. The male of the species generates vibrations of a tree branch with his legs, contracting and extending them approximately 12 times a second. These vibrations, called tremulations, can be detected by other male tree frogs on the same branch. It is not yet known whether the sensors which detect vibration are in the frog's skin, its vestibular system, or some other part of its anatomy. However this occurs, this input is sent to the frog's inner ear, where it is converted into electrical signals that travel to its brain for analysis. Depending on the pattern of vibration identified, the message communicated and received may mean, "Stay away. This is my territory. This is where I and I alone will call out to a potential mate tonight." Of course, the male receiving this message may respond with tremulations of his own, saying, "No, this is my territory. I am not going anywhere." When this occurs, aggression between the males follows to determine who will leave and who will stay and who will get to sing tonight for his mate. Spiders use their legs too, but they're not used to generate vibrations, but rather to detect them. They have sensory hairs on their legs called trichobothria that sense the vibrations of its web. Just as a microphone is an extension of the ear of a scientist, the spider's web is an extension of its vibration-sensing anatomy. Through its web, the spider can sense the approach and landing of potential predators and prey. The spider's ability to detect and analyze vibrations on its web has evolved to be so efficient that the sound-sensitive surface area of its web is up to 10,000 times greater than its own body size. In other words, it uses its vibration-based intelligence to answer when, what, and who questions. Did something just land on my web? Yes. When? Now. What is it? Living or non-living? Living. Who is it? Food source or assassin? Food source. Bats use a process called echolocation to find their prey. They do this by emitting high-frequency sounds that bounce off objects and return to their ears, where numerous receptors detect tiny frequency changes. The bat's brain then uses this information to create an acoustic map of its surroundings. Is it a tree branch or an insect? Insect. Is it a cave or a pool of water? Water. Whales are the Earth's largest living mammals. They live in the ocean in social groups called pods and use sound to communicate, navigate, and find food. Scientists at McMurdo Oceanographic Observatory study their vocalizations. Whales produce a wide range of vocalizations, including clicks, whistles, and pulsed calls. Clicks are particularly important for whales as they bounce off objects in the water and provide the whales with valuable information about the size, shape, and distance from an object. A whale receives sound through its lower jawbone, which is connected to its middle ear. These signals are processed by specialized sensory cells called hair cells and then transmitted to the whale's brain through its auditory nerve. This animation from the Museum of New Zealand shows how a sperm whale uses low-frequency sound to communicate, sometimes over considerable distances. Like a bat, the whale's brain can analyze the time delay between the click and the echo to determine the distance to the object. By analyzing the frequency and amplitude of the echoes, the whale can also determine the size and shape of the object. However, unlike bats, whales use a wide range of vocalizations for social communication and coordinated activities such as hunting. The question challenging scientists is determining whether the communication between whales constitutes language. This is a complex question. Clearly, whales, dolphins, and porpoises, and many non-human primates are communicating a wide variety of information through both sound and gesture. But is it language? Do they have vocalizations that have a fixed meaning? Can new vocalizations be invented to address real-time observations for which there is no existing vocalization? Do the sounds they make have a structure and a syntax? In other words, do these highly developed social organisms have language? The simple answer is to be determined. Science is always a work in progress. A related but even more complex question is whether the cetacean family of marine mammals are self-aware. Can they reflect about their experience? Do they experience emotions? Do they share their reflections and feelings with other members of their pod? For Homo sapiens, the clear answers to questions of consciousness is yes. We have language, which we form through acoustic vibrations. Speech. We manifest our language in waves of light, using gestures. Unlike any other species, our language can be represented. Through the medium of light, it can be written or signed. Or through the medium of touch, it can be represented in Braille. Our words live in our heads too. We're an ongoing internal dialogue, mainly in the form of vibrations, manifested as words, swirls and sentences that weave into paragraphs and paradoxes. Our intelligence addresses the same who, what, when, and where questions that the intelligence of other organisms ask. But, as far as we know, only humans can ask and form answers to how and why questions. How did the universe come to exist? How did life form? Why does it exist? Is there a purpose? We not only ponder these questions in the vibrational language of words, we search for meaning through the vibrational language of music. Music, such as the soundtrack to this video series, brings together all the elements of vibration. Molecules of air gain energy and character from the human voice, as well as the vibrations of each instrument. Spoken words elicit images in the brain and a profusion of chemical reactions in our bodies experienced as emotions. Maybe something like this: patterns of light we have seen through the Webb telescope that take us back, all the way back to the very beginning. What we have observed over the course of this video series is a process of matter coming to life and evidencing intelligence. Right from the outset, that process was set in motion just fractions of a second following the Big Bang, when the physics of the universe at a quantum level favored complexity rather than evenness. As life evolves, it explores, like a group of scientists in a lab with billions of years to do their jobs. Life discovers light and molecular signatures and vibration and much, much more.
meaning?
We have just scratched the surface of what life has discovered. Life has used these discoveries to get smarter and smarter in hundreds of millions of different ways. One of those hundreds of millions of ways is us. Humans are life forms that have developed hands with opposable thumbs and an information processing brain to use them and use tools that allow us to look up and to look down and to ask questions. What is all this? How does it work? Why does it work this way? Today's answer to these questions will seem rudimentary 1,000 years from now, as will those answers to the humans who ask and attempt to answer them 1,000 years later. Perhaps someday, when we learn to communicate well with other intelligent species who share our planet, or those who might come from another solar system or galaxy, these intelligent beings will offer their own questions and their own unique perspectives to the evolving discussion. Just as the universe will continue to expand, so will intelligence.